Welcome back to ECE 320A. In this short segment, I want to actually finish up sketching the Bode plot of a transfer function that we had initiated or started sketching in an earlier lecture. It's given by this equation on the screen, h of s, and it has one finite 0 at minus 0.1. It has a pole at the origin, a pole at minus 200, and a complex pole pair at minus 6 plus and minus j8. What I want to do is really these 3 points. I want to show how we will agree in this course to approximate the complex factors by essentially setting our damping ratio equal to 1, just to make the task of sketching the complex factor a little easier. Then we will go ahead and combine the individual terms that we've already produced for most of the factors in this expression, and then we'll have just a list of questions that one could possibly ask or address based on sketching or the sketch of this Bode plot. This is the system that we started with. It's in pole zero form to begin with. Again, it has the 4 poles and the 1 0 and then a constant out front. We factored out the constant factors or terms in each expression to try to give us a time constant form, or we've now normalized the constant factors in the linear terms and in the quadratic term to give us a constant of 1. And that left us with a gain of 0.02. We've sketched that individual component's Bode plot. We've sketched the individual Bode plot of the 0 factor, the pole at the origin, and the pole at minus 200. And what we want to do now is deal with this remaining factor, which is the complex factor. And in this sketch, this is now an S-plane sketch. I've simply indicated where one of those 2 poles, the second pole, is actually its mirror image below the real axis at minus 6 minus j8. And what we want to do now is show the agreement that we are going to agree to perform in this class to help simplify the sketch of that complex factor. Remember from earlier that this complex pole is a distance of 10 away from the origin. That's the hypotenuse of this right triangle with a real part of 6 and an imaginary part of 8. We have a natural frequency of 10, and the damping ratio is associated with this factored form of s squared plus 2 zeta omega sub n s plus omega sub n squared. And the damping ratio zeta can actually then, for complex roots, assume a value of zeta equals 0, which puts us on the imaginary axis with purely oscillatory roots, or we can then slide that all the way down to a zeta value of 1, and that gives us then critically damped poles. And that's what we want to do in this class. We want to go ahead and agree, no matter where we have complex poles located on this range from zeta equals 0 to zeta equal 1, we will agree to go ahead and set zeta equal to 1 to approximate that set of complex poles as if it were 2 real poles at a distance omega sub n away from the origin, right on the real axis. Meaning what we are doing is we're starting with, in this numerical example, an expression of s over 10 squared plus 2 times 0.6. There's our zeta value, s over 10 plus 1. And what we are agreeing to do is, no matter what this zeta is, we are going to go ahead and set that equal to 1. That's for this class, that's not anything that you really can say you can do for any particular system. No, that's just this class, a way to approximate these complex factors so that now we have a perfect square with real roots associated with that perfect square. So that now we have a factor, a quadratic factor, that in fact is just a squared linear factor. With that particular approximation, we can now sketch the magnitude and phase of that repeated linear factor. In this case, I hope it's clear that we now have a break frequency of 10. This is, again, our break frequency, and for a linear factor, we simply are 0 dB until we reach that break frequency. Now, because we are squaring that, we are not going down at minus 20 dB per decade, but in fact we're going down at minus 40 dB per decade, which means that if we go 1 decade beyond 10, we have now reached 100, and we would be at minus 40. And now we can connect a straight line, and that continues to simply slope at minus 40 dB per decade for all frequencies beyond the break frequency of 10. The phase, so this is now the magnitude of that factor in dB. If we want to look at the phase, again, we have a linear factor just doubled or duplicated. Everything is centered around, for our phase, it's centered around the break frequency of 10. And everything happens between this 2 decade, or within this 2 decade range in our approximation. And each of these linear factors, we have 2, both of them at 10. Each of those contribute 90 degrees of phase, and since it was a pole factor, we would be going down. And they do it right at the exact same interval. And a decade before 10, we are at 0 degrees. A decade after 10, we are twice 90 in the negative because it's a pole factor. So we're down here at minus 180, and now we simply connect those two straight lines with a sloping straight line, and we would like for this to be at minus 90 degrees right at the break frequency of 10 radians per second, and in fact it is, if you've sketched it properly. So this is now our phase curve for that complex factor that we are approximating in this fashion. And with zeta varying between 0 and 1, it will just make this straight line approximation a little bit more rounded, so that when you have a zeta value of 0, you actually immediately transition from 0 degrees to minus 180 degrees right at the break frequency. And now we're sort of showing this limiting case, or this ideal case, of a zeta value of 1 for a damping ratio of 1. Let's now combine all of the individual terms that we have sketched previously associated with that h of s written in time constant form. We now want to actually identify or have quite a few decades of frequency, because this particular transfer function has poles and zeros that span a wide range of frequencies, so that now we are going maybe I should have had it go a little bit further than I did, but let's just say that this is now the magnitude of h of j omega in dB. So I will change that. I will change these so that I end up at 10 to the fourth, and I'm going to start at 10 to the minus 3. And let's say that this is now our 20 dB, 40 dB, 60 dB line. Minus 20 dB. Obviously, these are supposed to be uniformly positioned relative to the 0 dB line, which is right here in the center. This is now plus 20, plus 40, minus 20, minus 40 dB. Remember, our constant term was at minus 34. I will draw these in blue. Let's just say this is now our constant term. We then had a pole at the origin, which, well, let's go ahead and do this maybe in the order that we did it. We had a 0 that had a break frequency of 0.1 or 10 to the minus 1. That now is 0 until we reach that break frequency, and then it starts going up at 20 dB per decade. That's the 0 factor. We only have one, so I'll just call that the 0. We had a pole at the origin, which goes through 0 dB at 1, and to the left, or for lower frequencies, it's going up. It's sloping negatively, and so we can now introduce that to go through all of these dots. Again, if I had sketched that properly, that would be a straight line. Then we had a pole at 200, which is 30% of the distance between 100 and 1,000, and then at 2,000 it's down to minus 20, and it keeps sloping at 20 dB per decade. So this one is going up plus 20 dB per decade. This is going down at minus 20 dB per decade. And then we had our quadratic factor that we are approximating as 2 real poles, and it broke at 10. And so then it was going down to minus 40 at 100. This green curve is not very straight. Let me try to make it a little straighter, and let's say this is now minus 40 dB, and then at 1,000 it would be at minus 80 dB. Let's go ahead and say that that's approximately right here, so that now that is our quadratic factor. What we want to do is now combine all of these with respect to frequency. So if I were to simply say, oh, at this frequency, what is the magnitude? The only two individual terms that are active, in a sense, at that point is the pole at the origin and this constant term. I've sketched this to where, or that highlighted yellow line is intersecting the pole sloping pole factor magnitude term at about plus 38, and the minus 34 is the constant. So in fact, we would have something a little bit above 0. So if I was accurate, I would say it was about right there, or plus 4. And if we look at exactly 0.01, or at 10 to the minus 2, we should be at 6 dB because we have plus 40 and minus 34. And then right at when we get to 0.1, we have a gain on the pole factor of 20 and a minus 34, so we should be at minus 14 at that particular point. So let me say that we're right there, and we would then be sloping down with a slope of minus 20 dB per decade due to the only thing that's sloping, which is that pole at the origin. But once we hit a frequency of 0.1, or 10 to the minus 1, we have the pole at the origin sloping at minus 20. We have the 0 at 0.1 sloping up. Those slopes cancel, and we then go flat until we reach the next kink or break, and that's actually occurring here at 10. So I'm going to be flat at minus 14 dB until I reach this point, and at this point, the only thing that's sloping is that quadratic factor, and that's going down at minus 40 dB per decade. So at 100, I would be 40 dB down from, let's say, minus 14. So now I'm minus 54 dB, or I should just be going parallel with this sloping line due to the complex pole approximation. And I will continue with that slope, which is 40 dB per decade, until I reach the next break frequency. And at that point, I now have not only the complex pole factor contributing minus 40 dB per decade, but I also have an additional pole now kicking in. So beyond this point, I should be sloping at 60 dB per decade. Here I have minus 20 dB per decade prior to 0.1. I'm then flat with my slope until I reach 10, which is where the complex factor kicks in, and then I'm going down at minus 40 dB per decade, and then above 200, I'm now sloping at minus 60 dB per decade for all frequencies beyond that. And that's now the magnitude plot in red of the result, and that should be somewhat consistent with this magnitude plot from the true Bode plot from MATLAB. If we now look at the phase curve, again, let's remember that we need to have 7 cycles of frequency, and we're starting at 10 to the minus 3. And ideally, we would have these lined up with the magnitude plot so that we could compare magnitude and phase for all the frequencies in question. In the phase curve, our gain was giving us 0 degrees, but then we had a 0 factor that again is going to produce phase over a 2-decade span, and it will be centered at the break frequency, which for our 0 was 10 to the minus 1. So that now we are going to, for our 0, going to be moving between 0 degrees and plus 90 degrees. The 0 then gives us a phase curve that looks like this. This is our 0. Our pole at the origin is always going to be at minus 90 degrees. Our pole at 200 will now contribute phase between 20 and 2000. And again, it will contribute minus 90 degrees. Whoops. I need to make it a little bit better or more accurate than that. So I need to go over here. And then the slope stops contributing, and we then have, so this is the pole at minus 200, and finally we have our quadratic pole or complex pole that's centered around 10, and it kicks in a decade before and it kicks off a decade after, and it transitions between 0 degrees and minus 180. And that is now the complex pole. The phase curve, then, we need to go back to a low frequency where there's not a whole lot happening. We only have one pole contributing, and that's the pole at the origin. It's now starting at minus 90 degrees. Then once we reach omega equal to 0.01, the zero factor starts contributing a slope. But remember, we have to turn these slopes off. They don't just keep going. But this one is only on, and it's only on by itself. So that will take us right up to 0 degrees. And at that point, the complex pole kicks in, and it looks or works just by itself until we reach this break due to the phase of the pole at minus 200. And once we reach that point, I shouldn't have been erasing this. So here is our complex pole. Once we reach that new break frequency, our slope needs to change. We will now go down a little steeper, but let's then say, where are we going to ultimately end up? We are going to end up with a minus 90 from the pole at the origin, a minus 90 due to the pole at minus 2000, plus 90 due to the 0. So one of those 90s will be canceled. We now are at minus 90, and we also have this minus 180. So we are actually, once every term has been kicked in, we will be at minus 270 degrees beyond, in our straight line approximation, beyond 2000 radians per second. Now, after this, and notice that the complex pole factor quits sloping beyond 100, and at that point then the only thing sloping is this pole at minus 200, and that changes at a slope of 45 degrees per decade. So right at 200, we should be halfway between minus 180 and minus 270. So I'll use that as sort of my guide. And this is now where we should be sloping a little bit steeper than just the complex pole, so that at that point we're sloping at minus 90 and minus 45, or minus 135. Here we are sloping at plus 45 degrees per decade. Here we are sloping at minus 90 degrees per decade due to the complex factor only by itself. Here we are combining the complex factor and the pole at minus 200, and the pole at the origin and the 0 have already canceled each other out. So this is now a slope of minus 135 degrees per decade, and right here we are back to minus 45 degrees per decade because the quadratic factor's phase contribution has stopped contributing beyond 100, and we end up at minus 270 degrees. This red curve then gives us the final phase of the transfer function h of j omega, and that hopefully looks somewhat like this phase curve here. You can see that beyond 1,000 we're getting very close to minus 270, and that's what we have here. It starts to build the phase or get closer to 0, and by about 1 radian per second it's getting close to 0, and in our straight line approximation we have it going right to 0, and then it transitions back and bends around to get us back to minus 270. Some questions that someone could maybe ask relative to this sketch, or to see if you really understand this concept of a Bode plot. Somebody might ask, what is the magnitude slope at, let's say, low frequencies, or high frequencies, or maybe even between. Let's say omega equal to 0.1 and omega equal to 1 radian per second. In this case, for this transfer function, low frequencies, and now we're dealing with the slope of the magnitude, low frequencies are anything that are really less than where we start bending or breaking, and that's occurring right here at 0.1. This would then be our low frequency range. Our high frequency range would be over here after everything has started to break, and that's going to be beyond 200. So here would be our high frequency range, and things between would be this intermediate frequency range. But in the low frequency, what is the slope of our red curve? That's now minus 20 dB per decade, because the only thing happening at that point is the pole at the origin. So in this case, we could say that at low frequencies we now have a slope of minus 20 dB per decade. At high frequencies, we are now looking at a net pole of 3 poles. We had 4 poles total with 1 0 total, so the pole 0 excess allows us to conclude that at high frequencies we effectively have 3 poles, and each of those poles produces a slope of minus 20. 3 times minus 20 gives us minus 60 dB per decade, and we could read that off from our sketch, and that's another way of thinking of that is we are using the pole 0 excess, which is 3, and 3 times minus 20 gives us that answer. Then we might say, what's the magnitude slope between 0.1, which is right here, and 1 radian per second. Whoops, I'm on the phase curve, so let me erase that. Didn't go far enough back. Here I want to know what's happening to my magnitude between 0.1 and 1. And if I look at the red curve in that frequency interval, my magnitude is not sloping at all. It has a 0 dB slope, and that's what I could then say to answer this question. The magnitude slope between omega equal to 0.1 and 1 is 0 dB per decade. And I could answer similar questions regarding the phase. For example, somebody might say, what is the phase at low frequencies? And again, in the low frequencies, we may have to go a decade below a break because that's when the phase starts kicking in. And likewise, for high frequencies, we may want to go a decade above where the break frequency is of the last thing that's happening. In this case, now low frequencies are occurring less than 0.01 or 10 to the minus 1. High frequencies are now occurring beyond 2,000 radians per second. And we might be saying then, what is the phase for low frequencies? If we look at the red curve, it's starting at minus 90 degrees. So this is now minus 90 degrees at low frequencies. The phase at high frequencies, that again is associated with the pole zero excess, and our pole zero excess is 3. Each of those poles contributes 90 degrees. They're in the basement, so they're minus 90 degrees, and we have 3 of those, and the red curve does in fact end up at minus 270 degrees, consistent with that pole zero excess strategy of determining that value. So those are some questions, some concepts that you can extract from these Bode plots and the information that we might be looking to determine from these transfer functions or frequency responses, which are contained in the Bode plots for these transfer functions themselves.